Hi, I'm Christian, and I would like to share with you some information about how to share large correlative microscopy datasets. Two disclaimers. One, this talk is obviously limited to things that I'm aware of and that I am using, so please don't feel offended if your solution, which may be even much better, is not part of this talk. Secondly, we are now having July 2025. And as we are living in a very fast developing world in terms of technology, if you watch this video much later, there's a high chance that some things will be outdated. With this, let's start. When thinking about sharing image data, one important consideration is where to store it. The classical place to store it would be your file system, where the limitation is that typically for security reasons, this is only accessible within one institute. Another option is a database. For microscopy data, the most popular one is Omero, that has the advantage of allowing you to keep track of metadata and data relations, possibly allowing you more flexible sharing with colleagues within the institute. Sharing outside the institute might also not be easy. This will depend on your specific IT setup. Potential disadvantage is that applications that want to read from Omero need to know how to talk to the Omero API. So it will be not as easy as just reading from a file system. If you just want to share small text files, and that will be also relevant later, then a very good place is GitHub, where you have versioning and everything is readily publicly accessible. However, sharing big image data is not possible there because they only support small text files or small files. Then a very important other way of storing data are so-called S3 object stores. They have been popularized by Amazon, who developed this to share data in the cloud. So you can share your data via URLs. And the good thing is, at least your IT department, at least ours, will probably, if they build such an S3 object store for you, also allow you to share data with external people. And the reason is that this can be made much easier secure than a file system. So I highly recommend checking with your IT department if something like this could be set up or is maybe already existing. Now, the other important thing is the data format. So you may be familiar with TIFF or MRC or others. There are many. The most important one for this talk is a relatively new one. It's called OMISAR, and it has been specifically designed to work well with these aforementioned S3 object stores, and specifically for partial access. That means you don't download the whole data set, but just chunks of it, namely the ones that you currently want to look at or work with. And the implementation of this is very simple. Each chunk is one file or one object or an object store, which makes it very easy to download many of them via HTTP. The other important thing is support for multi-resolution, like Google Maps. If you zoom in and out of your image data set, it can fetch data from the appropriate resolution layer, which will make the downloading and rendering much, much faster. One easy way how you can play with this yourself is using the tool Fiji, which you can install. And in this, it will come already with the plugin, the Big Data Viewer, and then HDF5 N5 SAR OME and GFF Viewer. So you can just open that. And then you can, for example, copy and paste the URL below in there and click Detect Datasets. By the way, this data is hosted at the Bioimage Archive in an S3 object store. And this was kindly provided by Anna Steyer from EMBL. So if you look at this, you actually see the multi-resolution pyramid. So the highest one here having most pixels and being also the largest, something probably too big for your laptop. And then smaller ones, typically downsampled by factors of 2 in all 3 dimensions. If you now click OK down here, Big Data Viewer will open and you can freely browse very smoothly through this image. And the trick really is, as mentioned, it will only fetch data from the appropriate resolution level depending on your zoom level, and then also only the chunks that intersect with your current viewing plane. Again, emphasizing, even though this looks here as if there is one folder with 6 files, that's not the case. Each of these resolution layers, like for example here 2, is again a folder containing many, many files which correspond to all these individual chunks. They're just not rendered here in this GUI. Okay, now if you want to share more than one image, a very important concept is JSON. So JSON is a text format for describing data, and it's used a lot, specifically also in the internet. It's based on key value pairs, where the keys here in bold can be free text. The values can be text, numbers, or arrays. Here, for example, is an array with the brackets. So I just made up here something that could describe an image data set that's composed of an image and a segmentation. And to make it more interesting, I'm pretending that this segmentation did not segment the whole image, but just a part of it. So as you can see, I say now each image can have some free text description, but also a path to where it's stored. Here it's on S3. The segmentation is also an image, but this is not stored in S3, but somewhere locally in a folder called images. Now, the other interesting thing here is this affine tag or key, which can be used to describe spatially where this partial segmentation lives in the global coordinate system of the image. So the idea is the image would be bigger than the segmentation, and with this affine transformation, you can specify how to move it there. So that would be typical ingredients that you need to share correlative image data in JSON. Now, the tricky bit is these keys, you have to define them. And the way to properly define them is a so-called JSON schema, which is another text file that has to be somewhere, and that defines valid key value pairs for a certain subset of JSON files that then work with certain applications. So that's very important. For example, some people may think they want to call it path, and others may think they want to call it URL. This has to be defined somewhere, and your software needs to understand this. Now, one example application that makes use of all these concepts is called MoBIE, which has been developed by myself and coworkers. It's a Fiji plugin that you can install. You can check this QR code. And it's making heavy use of the Big Data Viewer tool that I just introduced before. So MoBIE basically can compile images, tables, and metadata, and it also makes use of JSON files to describe how everything is linked together. Supports several modes. Could be that everything is saved on a file system, so the metadata, tables, and images, or everything is in an S3 bucket object store. Or what we use quite a lot is this mode where all the small files like the tables and the metadata are on GitHub, and then the big files, the images, are stored in a S3 object store bucket. You can try to explore such a project. So for example, this one here is stored or represented in this GitHub URL. So if you say open MoBIE project and you put this URL, it will open and you will be able to browse data. So for example, it's a big volume EM data set with segmentations. And then there will be drop-down menus where you can actually, for example, also say, hey, I want to look at figure 2D nephridia segmentation. And then all of the things here on the right will pop up. You will see the segmentation also in 3D. You will see the tables. and so on. And if you're interested, all of this whole view here of this correlative big data set is defined in this dataset.json in a certain JSON schema that you can explore here at this URL if you're interested. Another tool, not developed by me, but by people at Google, is called Neuroglancer. And that's a tool that runs in the browser. And it also makes use of JSON files to define correlative data sets. So here's actually a real Neuroglancer JSON. And you see it's very similar to what I presented in the beginning. So here they don't say URL or path, but source. And in this case, it's pointing to data stored on S3 object stores on EMBL. Actually, again, a volume EM and a segmentation. And here's a few other key value pairs that you can observe. Now, what's very convenient here is that actually a Neuroglancer URL can be composed of this prefix and then the actual JSON text in the same URL. That means you define everything, the application and what you want to look at in one URL, which is kind of cool. And so, for example, if you scan this QR code down here, actually this view will open up on your computer or mobile phone without needing to install anything. Okay, one more comment about OME ZAR. So in fact, the specification of OME ZAR allows that one OME ZAR can contain multiple image data sets. So if you look at the folder structure here, and there's actually also made use of JSON again. So this zar.json defines the first image, and actually the subfolders here are the resolution pyramid. And then there's another subfolder, seg. This is actually free text, could be anything. Maybe there's a segmented file. And again, you have the JSON and the resolution pyramid. And you can have many of this. So that means in principle, actually, it's possible to use one OME ZAR folder to ship a whole correlative data set. Well, this is very handy. I think there's also some challenges. For example, if you copy and paste the above URL into some viewer application, it might be not immediately obvious whether it should open all of these images or just some of them. And also, another consideration is the segmentation you might produce or you will produce later than the actual image. And if you then add it into the container, then actually the content of this container changes. And if that has been already registered somewhere, then things become a bit messy. So you have to be a bit worried here about the data management. It's not so easy now because there is one kind of thing that contains many and they might even change. So I think there one has to be a bit careful. Okay, another thing I would like to mention is a row crate. It's another JSON. But as you can see here on the right, it's a little bit more complicated. It also has these add symbols. So I will just read here what's written on the left, and then you know why I'm mentioning it. So row crate is a community effort to establish a lightweight approach to packaging research data with their metadata. This is, of course, something we like, right? And then row crate metadata.json describes files, directories, and URLs, as well as relating them to things in the world. Example, people and instruments. Again, sounds very useful, right? So here on the right is again some invented example how one could use this. And you can see that in principle, one can express relations like this image was generated by a certain microscope, and you can then actually have a URL that defines this specific microscope. So row crate is definitely something to look for, might be used also in the bioimaging community at some point. Disadvantage is that these JSON files, as you can see, become a little bit harder to read. So that's why not everybody is sure whether we should go for it at this moment. So let me summarize this first part a little bit. So I think the really, really good news is that there's a really broad adoption of OME-SAR and also of OME-SARs hosted on S3 object stores. Here's an excellent publication that summarizes many tools that use OME-SAR. So here in this drawing, you can see WebNozzers, which is in fact a commercial application, but it's also supporting the open source standard and even supporting them actually quite a lot. Then here is the MoBIE Fiji tool again, and there is Neuroglancer. But there are actually many more, as you can see in this publication. Okay, what about the JSONs? So good news, JSON is consensus, right? It's used by many tools. The maybe less good news is that the schema that all these tools use are different. So Neuroglancer, MoBIE use different ones. Unfortunately, the row crate one will maybe look again different, and Big Data Viewer doesn't have one yet, but might have one soon, developed by Tobias Peach, but might again look a bit different. So what can we do about this? So one thing we could do is work on interoperability. So for example, as good as possible, make Big Data Viewer read and write Neuroglancer JSONs is something that Tobias is considering. So Tobias is the developer of Big Data Viewer, for those of you that don't know. Then Norman, who is the head of WebNozzers of this company, together with people, including me, in fact, suggest to work on a standard JSON schema that maybe then many tools would support. If we do that, we for sure will need also a standard for transformations, because what will be important for correlative data is to decide, for example, how to store all these affine transformations that put things on top of each other in the correct way. And luckily, there we have John Bogovich from Janelia in the US, who is working on such a standard. He is, for those of you that don't know him, the developer, BigWarp, a very useful Fiji plugin for actually registering big image data sets, among many other things that he's doing. Okay, could we do something in addition to JSON? So this discussion came up when I talked with people that said, well, sometimes I just want to manually change how my correlative data set looks like, and they say they always fail manually editing these JSON files. And I admit it's a bit hard. I mean, you have to get all these brackets and commas and keys and values correct, which might be not so easy. So what else could we do? So what I then explored is how much can we actually do with a simple table? And that gave rise to what is now called the MoBIE collection tables. And the idea is relatively easy. So there must be always one column that's called URI, and that's again the source path column that we have already heard about. And here is actually several images. Should be all OME-SARs. It's just for legacy reason that some of them are actually some other file format, but you could just consider they're all OME-SARs. And then there's a column called affine. And there you can say how to register these data on top of each other. And there can be also arbitrary other columns where you maybe just store some information, and a color column where you can give the rendering. And if you open this table in MoBIE, you actually will get this rendering of a correlative light and electron microscopy dataset, because this is all you need to specify. And you also still have the table, which is convenient. You so, for example, see this dataset here should contain some mitochondria. What is practically very convenient, actually, that it's possible to directly open a Google spreadsheet. So that makes, and this URL actually points to one. This makes it particularly easy to share this with other people, because you don't even have to send files around. You can just send the link to this spreadsheet. that can be directly opened. Another example, so we are currently supporting 3 data types. One is called intensity, so this would be normal images. One is called labels, so this is segmentations. And actually, if it's a segmentation, we support also a column called labels table URI. So there can be a link to a table that contains, for example, measurement results about the cells, like how big they are and also where they are. And we also support spots. So this is a very simple table where you can have just spots, and that could be used to annotate certain locations in your image. For example, here the eye and some muscles. And then if you click, in the application on any of these rows, it would go there, and then you can see how do the muscles look like. What is kind of neat, I mean, could be useful, something I found out actually. So these spots themselves are actually just another tab in the same Google spreadsheet, and you can link it like this. So that means, in fact, also this table here with the labels could be in the same Google sheet. So you could actually have one Google sheet that contains quite a lot of information, which could be convenient. Okay, another thing that many people find useful, and it's also supported by MoBIE, is so-called grid views. So in MoBIE, you would add another column called grid, and then all this data would be shown simultaneously and be laid out in a grid with a tile size that works such that everything fits. Here you see the images have very different sizes, so that's why it doesn't look so pretty. The data itself, however, is very pretty. So this is the open organelle data from Janelia, which is relatively famous. And in fact, this is 3D. So all of these grid tiles are 3D, so you can zoom in and out and move up and down in 3D. So that's nice to get an overview of a big data set, right? And to just see what you have, and you can move around and so on. And since this is so useful, there are actually other tools that do something very similar. So there's Zarcade from Janelia. You can check this out. That works on similar data and does actually a web rendering. And the biofile finder from the Allen Institute is also a very interesting development along similar lines. And I encourage you to check this out. Okay, coming to the end, a few other related developments. So what's so cool about these web solutions is, right, that you can just send people a link in your email and they directly can see something. For example, that makes Neuroglancer so attractive. So what I found kind of intriguing is that people thought, hey, can't we also do this for Fiji? So Marwan from Janelia, together with Tobias, in some aspects, they are actually exploring whether they could make it work that you can send around links like that start with Fiji, and then you can click on it, and then your computer will automatically open Fiji with a certain application here, for example, Big Data Viewer, and there could be then a JSON that tells Big Data Viewer what to open. So you would have a Neuroglancer kind of experience, but with ImageJ on your computer. So this doesn't work yet, but I think this is a very fun idea. Then another thing, so OMISAR support is really increasing. So for those of you that like Blender to make beautiful renderings, there's good news. So you can check out this publication here and learn how to make beautiful correlative image renderings of OMISAR data in Blender. Then spatial data. I think this is an interesting Python package. So, and as you see again, OMISAR and JSONs are involved. So I think the tools I have showed so far, like Neuroglancer and MoBIE and so on, they are actually only visualization tools. But sometimes you also want to do more, right? You want to actually really work with the data and measure stuff, or do downstream tasks. And for this, I think the spatial data package is very interesting. So they support many of the data types that we need, right? Spots, tables, labels, images, and they also support coordinate transformations, and everything can be rendered in the Python Napari viewer. So I think this is something definitely to look for if you really want to work with your data and do, for example, some statistical analysis. Okay, and that's it. So here are my acknowledgements where I would like to apologize that they are super incomplete. First of all, funding. So NFDI for Bioimage and the Jen Zuckerberg Initiative, thank you very much for support. I would like to thank Konstantin and Kimberly for working a lot with me on MoBIE. Then Stefan Saalfeld, Stefan Preibisch, and Tobias Peach for enabling all this amazing big data rendering in ImageJ and Big Data Viewer. Then probably also very mainly Josh Moore, who is really driving the whole OMESR development. Thanks a lot, Josh, for doing this. I know it's hard, but it's very amazing as well. Then Norman, I already mentioned a few times from WebNosos, who is really helping also a lot here. And also John, as mentioned, is helping actually on several fronts, OMESR development, but also helping with ImageJ related things. Okay, thank you very much for your attention. And if you have any questions, please let me know and get in touch. Bye-bye.